Okay. Good evening, students. So, shall we start the class? Yeah. So, am I audible to everyone? Yes. Anybody, please confirm it. Am I audible?
Yes, sir.
Okay. And my slide is my presentation so also visible.
Yes, sir. Visible, sir.
Okay. Good. So once again, good evening to everyone. So today we have a seventh class and second unit, that is a control of electric vehicles. So in the previous class, we discussed the types of the motor, which type of motor we can use for the AV application. And then we can start with the induction motor. So that is a basic fundamental of the induction motor. So basically there is a revised concept because induction motor and DC motor, that is like fundamental of the electric motors. So in the last class, we discussed the uh, fundamental and otherwise we can say the revise of the induction motor as well as the DC motor. Then we discussed the overview of the permanent magnet synchronous motor and brushless DC motor and SRM motor. Correct. So today's we are going to discuss the more about the like working principle of the permanent magnet synchronous motor and SRM motor, that is a switch reluctance motor. So is there any confusion, any doubts from the previous class? So in the previous class, we discussed the detail about the like brushless DC motor and the like overview of the permanent magnet motor and the like switch reluctance motor. So any confusion, any query from the previous class? Okay. So introduction of the PMSM drive. So as you know, PMSM and BLDC both are the brushless DC motor. So there is a PMSM and BLDC motor. PMSM stand on permanent magnet synchronous motor and BLDC stand on brushless DC motor. Both have a permanent magnet rotor. So on the rotor side there is a permanent magnet and stator it is a typical like the wound rotor, so it is the same like the we can say the induction motor stator, correct, but little bit different in the stator winding. So we can say in the BLDC motor there is a concentrated winding, but in the case of the PMSM that is your we can say the distributed winding. Okay, so we can say PMSM stator winding is a distributed. But in the case of the BLDC, stator winding, that is a constant. Concentrated winding, correct? So this is the major difference between the BLDC and PMSM. So BLDC motor is a permanent magnet brushless motor with a tapezoidal back EMF. So back EMF, that is a tapezoidal waveform because of the concentrated winding, correct? But in the case of permanent magnet synchronous motor, permanent magnet brushless motor with sinusoidal back EMF. Okay. So here is a sinusoidal back EMF and here is a tapezoidal back EMF. So in the yesterday class, we already discussed about this waveform, correct? So sinusoidal and the tapezoidal back EMF. Okay. So but both are the synchronous motor category. So we can say both are the synchronous motor category. But depend on the winding structure, we can say we can classify the PMSM and BLDC motor. So classification of the PMSM motor. So based on the direction of the field flux, okay, so we can say that is based on the direction of the field flux. So what type of field flux are there for the motor? Second classification, shape of the induced EMF. So what type of induced EMF? What is the shape of the induced EMF? And third type, there is a mounting of the permanent magnets. So how you are mount the magnets on the rotor. So we can classify the permanent magnet motor based on the three category. First category, second category, and third category. So in the first category, direction of the field flux, that is a radial field and the axial field. So suppose that is a field is produced in the radial direction, then we can say the radial field motor. And suppose flux is produced like axial, then we can say the axial field permanent magnet. Okay. Second one, there is a shape of the induced EMF. So we can say BLDC motor and PMSM motor. BLDC, there is a trapezoidal, and PMSM, there is a sinusoidal. Third one, there is a mount of the permanent magnet. So there is a surface mounted, otherwise the internal mounted. Correct. So we can say the inner rotor and outer rotor. Correct. So in the last class we discussed the inner rotor BLDC motor as well as the outer rotor BLDC motor. Same we can say inner rotor PMSM and outer rotor PMSM. Okay. So yes, is there any confusion for this classification? So we can classify the widely in the three categories: direction of the field, shape of the induced EMF, and mounting of the permanent magnet. Okay. Yeah, so pictorial view of the classification. So you can see figure number 1, three-phase stator winding of permanent magnet. So there is a distributed winding and concentrated winding. So you can say this is the distributed winding. It is the same like the induction motor. Okay, this is the same like the induction motor. So in the case of the induction motor, there is a distributed winding. So you can see this is the maybe the phase A. This is the phase A. Correct. So phase A is cover many pole. So you can see first pole, second pole, third pole, fourth pole, 5, 6, 7, and 8. So this 8 pole is cover the phase A. Similarly, there is a black color wire. It is also connected with another pole. Correct. So we can say that there is a phase A is distributed among all the poles. Correct. So there is a distributed winding in the PMSM. But you can see in the concentrated winding figure B, this is the BLDC motor and this is the PMSM. So you can see the BLDC motor, there is a phase A, only 2 pole is covered. So you can see pole number 1, pole number 2, and there is a phase A. Similarly, phase B, this one and this one, this phase and this one, there is a phase B, and phase C, this one and this one also, there is a phase, this one and this one and this one. This is the phase C. So all the winding there is a distributed, not the distributed, but it is a concentrated nearby the pole. Okay. So that's why we can say it is a concentrated winding. Okay. Yes. And so pictorial view. So figure number 2 of the pictorial view of the distributed winding, there is a PMSM. So you can see this is the PMSM motor, and you can see this is your concentrated winding. So it is a concentrated to the nearby pole only, not the distributed to entire the stator winding, stator pole. Okay. So that's why we can say it is a PMSM and BLDC motor. Please memorize there is a PMSM is a distributed winding and BLDC there is a concentrated winding. Okay. That is the most important part. In back EMF, in the case of the BLDC, there is a trapezoidal, and in the case of the PMSM, that is your distributed back EMF. So there is a surface mounted and interior mounted. So otherwise, we can say the outer rotor and inner rotor. So in the case of the surface mounted, we can say the outer rotor XD equal to XQ. So DX is reactance is equal to QX is reactance. Okay. In the case of the interior mounted, we can say the QX is interior greater than the DX is reactance. Correct. So this is the like fundamental concept. Suppose you are designed the like surface mounted PMSM motor, then you will get the XD equal to XQ, and where you can use the XD equal to XQ while you design the control algorithm for the PMSM motor, otherwise the BLDC motor. In the case of the interior PMSM motor, otherwise we can say the inner runner PMSM motor XQ greater than the XD, and this is the structure of the interior PMSM and the outer surface mounted PMSM motor. Okay. So XD and XQ both we can use in the while design of the control algorithm, correct? So comparison between the PMSM and BLDC motor, because both are the synchronous motor, both are the similar structure. Only difference is the stator winding, okay, and the back EMF. So we can discuss the comparison. So PMSM feed with the AC supply and feed with the DC supply. Yes, so that is a major difference. So we in the previous class we also discussed. Ultimately, we have to give the AC supply, correct? So in the case of the BLDC, we can say the electronics commutator. Electronics commutator, correct? But in the case of the AC, we can use the inverter again for the controlling operation, correct? Sinusoidal flux density, yes, we can say that it is because of the distributed winding, we can get the sinusoidal flux density. Square flux density because of the concentrated winding. Back EMF is sinusoidal because we have a flux density sinusoidal, so we will get the back EMF is also sinusoidal. Back EMF is trapezoidal because there is a concentrated winding. That's why back EMF is your trapezoidal. Current is sinusoidal driven by the controller, which make the controller more complex and the costly. Simple language, you can say, because of the sinusoidal nature, controller is very complex, and suppose it is a very complex, then we can say it is a very costly. Current is a trapezoidal driven by the controller, which make the controller easier and cheaper. So simply we can say BLDC motor is easy to control the speed and torque, but PMSM is a typical, correct? For the equal resistive losses, power density is less. Suppose you are comparing the equal resistive losses, power density is less. And for the equal resistive losses, power density is a 50.4% higher than the PMSM. Okay. So that's why we can use the BLDC motor in the case of the two-wheeler and the three-wheeler. The conduction and the switching losses are high because of the three-phase transistor in the inverter conductor, correct? The conduction and the switching losses are smaller because of the only two transistor in the inverter conductor. So at a time we can operate the two transistor in the case of the BLDC motor. Otherwise we can say in the case of the BLDC motor we can operate at a time two phase only, not the three phase. But in the PMSM we can operate the continuously three phase. Okay. Torque ripple due to the commutation is current is low. Okay, so in the case of the PMSM, torque ripple is less. Torque ripple due to commutation current is high because of the trapezoidal waveform, and at a time we can operate the two phase. So torque ripple is high compared to the PMSM. The coil in the case of the PMSM, coil of the distributed winding are not coaxial. They are rather than distributed in the various slot along the air gap periphery. Yes, so winding is distributed around the stator slot. Okay, the coil is a concentrated winding are the coaxial. This means all the winding has the same magnetic axis. What is the back EMF equation? So back EMF equation is a 4.44 and phase. So there is a number of phase. Sorry, number of conductor for one phase, correct? So n is a number of conductor, correct? So n phase number of conductor, that is a per phase. Okay, so n phase, that is a number of conductor per phase. F is a frequency and phi, that is a your flux. Okay, so there is a EMF equation 4.44 n phase, that is the number of conductor, into the frequency into the phi, there is a flux. In the case of the BLDC motor, back EMF, that is a 4.44 n phase, phi, F, Kp and Kd, where Kp there is a pitch factor and Kd there is a distributed factor. Because of the concentrated winding, we have to consider the pitch factor as well as the distribution factor. Okay, so Kp there is a pitch factor and Kd that is a distributed factor of the machine. Okay. Torque equation for the PMSM, there is a 3 by 2. P by 2, P is a number of pole, not the pole pair. P is the number of poles. Okay. Lambda F flux density minus LD minus LQ. So dx is inductor and qx is inductor into ID. Dx is current into IQ, that is a QS6 current. So we can say we have to convert the three-phase quantity into DQ quantity for the better control approach. So this DQX is we already discussed during the first semester in the analysis of the electric machines, correct? If you forgot this concept, then please revise that concept, correct? So ultimately we have to convert the three-phase quantity into two-phase quantity for the better controllability, okay? But in the case of the torque equation, so torque is equal to EA into IA. EA, there is a back EMF. IA, there is a phase A current. EB into IB, there is a back EMF of the phase B and current of the phase B plus EC into IC divided by omega M. Correct? So otherwise you can say simply torque is equal to EI divided by omega. Okay, so there is a voltage current divided by omega. Okay, so what is the value of EA? EA is nothing but a function of there is a function theta r plus into lambda f into omega m, that is your EA. Okay, similar for the EB and EC. So there is a phase A, phase B, and phase C. So this is the your torque equation. Yes. So till now, any confusion for the both motor? There is a PMSM and BLDC motor. Any confusion here, student? Is there any confusion, any query for the PMSM and BLDC motor? Okay. If no confusion, then we move ahead with the last motor. There is a switch reluctance motor. Okay.
Sir,
Yes.
if ये maybe the MMF,
Yeah, you can consider the MMF because there is a function, correct? So function is maybe there is a MMF function because theta r, there is a rotor theta, correct? So we can consider the MMF. MMF, there is a nothing but N into I. N into I, where N is a number of conductor and I is a current, correct? So you can consider because there is a theta r. Yes, you can consider. Any more confusion? Any more doubts? Is it okay?
okay, sir.
Yeah. So MMF is a magnetomotive force and is nothing but number of conductors into the current, how much current is flowing for that particular phase. Okay. Yes. Now, last motor, there is a switch reluctance motor. So normally people use the like induction motor, PMSM, BLDC and switch reluctance motor. So recently in the Tesla's used the switch reluctance motor for one of the four-wheeler vehicle. Okay. Yeah. So what is a switch reluctance motor? So switch we know already, correct? So switch is nothing but on and off. So we can say switch. Reluctance, any idea what is a reluctance? Motor we know motor is nothing but mechanical device, electromechanical device. So it is a convert electrical energy into mechanical energy. Switch is nothing but simple switch. We can say on and off operation. So third term there is a reluctance. What is the more meaning of reluctance? Then we move ahead with the detailed analysis. What is the meaning of reluctance as per your knowledge? Any idea?
To oppose magnetic flux, sir.
To oppose?
Flux, I think. Magnetic.
Simply magnetic resistance, sir.
Magnetic resistor, yeah, oppose the magnetic flux. Both are the good, both are the correct. So reluctance motor is a type of the special electrical machine. It is the same like the PMSM BLDC motor. So it is under the special electrical machine category. That consists of the rotor and stator. Yes, because of the motor, we have two major components, rotor and stator, similar to the other motor. Okay. It is used to convert the electrical energy into mechanical energy. Yes, because of the motor. Reluctance motor is typically has the lagging power factor. You know, synchronous motor we can operate the both lagging and leading, correct? So we can operate the both leading and lagging quantity. But synchronous, this switch reluctance motor we can use for the lagging power factor. and it is efficiency range from 55 to 75%. Okay, so that is one of the major advantage of this switch reluctance motor. It construction reassemble that of the single phase induction motor, but it is working simple is different. Okay, so working principle is different. Otherwise, we can say it is the same like the induction motor. But this switch reluctance motor under the category of the synchronous motor. Okay, reluctance motor offer the high power density at low cost, making them suitable for the wide range of application. Because of the reluctance mode, because of the high power density, we can use in the various applications. Okay, so this is the not a switch. So spelling is a switch. Okay, switch reluctance motor. Okay, so that is a switch reluctance motor. So you can see the construction of the SRM motor. So this is your stator part. Okay, so this is your stator pole. You can see this is your stator pole. It is the same like your induction motor. This is your stator frame. So we can see the outer frame. So for the support of the stator winding, this is your stator core, and that is a laminated. Why lamination? Any idea why we have to laminate the stator core?
To reduce the eddy current loss, sir.
Yeah, so reduce the eddy current losses and hysteresis losses. Correct. So we have to laminate the like stator winding as well as the rotor winding if we have a rotor winding. So we can reduce the eddy current losses and the hysteresis current losses. Okay, so this is the stator core that is laminated. Main winding, that's a copper. So on the stator side we have a main winding, so we have to give the power supply, and that is a material designed by material of the copper. Okay. Now rotor, so this one is a rotor. You can say green color one. That is this one is a rotor. So rotor, there is a square cage. So there is a similar to the induction motor, and that's the material is a ferromagnetic material. Okay. Normally during the interview they are asking the which type of material used to design the rotor. Okay. So there is a ferromagnetic material, and this is a copper bar. So we have to add the copper bar so we can get the like more what we can say more power. Correct. So there is some mechanical power, otherwise you can say the more torque. Okay. So this is the typical structure of the your switch reluctance motor. Correct. So on the rotor side there is a no winding, only copper bar is there, otherwise the aluminum bar is there. Okay. So switch reluctance motor again. Switch reluctance motor work based on the variable reluctance principle, and reluctance is nothing but that is here oppose the main flux. Otherwise, we can say the mechanical resistor, correct? So some students said it is a mechanical resistor. Okay. So what is the property of the resistor? Resistor is oppose the current in the electrical network. Okay. But in the case of the magnetic circuit, reluctance that is oppose the main flux. Okay. So that is your reluctance. So switch reluctance motor that is operate based on the variable reluctance principle. The rotating magnetic field is created with the help of the power electronic switching circuit. So this one is the most important part. So how we can generate the magnetic field? Because on the rotor side there is a no magnet, no winding, only like ferromagnetic material bar. Correct. So how we can generate a magnetic field? So we can generate the magnetic field by turn on and turn off of the power electronic switching. Correct. So we have a 6 switch, we have a 8 switch. Yeah, 4 switch, depend on the application, depend on the converter, and depend on the motor. So we have to operate the switch one by one, and we can generate the magnetic field. The main concept is the reluctance of the magnetic circuit depending upon their air gap. So how much air gap between the north pole, that is a stator, and south pole of the stator. Okay, so there is a how much air gap. So we are trying to put keep the like minimum air gap. Hence, by changing the air gap between the rotor and stator, yes, because of the change in the air gap between the stator and rotor, we can change the reluctance of the motor. Once you are able to change the reluctance, then motor is able to rotate. Okay. So ultimately, what is the use of the power electronics converter switch? So that power electronics converter switch, it is a use to change the reluctance of the motor. Okay. Reluctance is nothing but a resistor to the magnetic flux. Yes, as you said, it is a magnetic resistor. Oppose the magnetic flux for the electrical circuit is a resistor and magnetic circuit is a reluctance. Okay, so we can say the R for the resistor, and S is a reluctance. Okay, so R that is a resistor and S that is your reluctance. So construction of the switch reluctance motor. So what is the construction? So you can see, so this one is a rotor part and this one is a stator part. Okay, so here I denoted the like A phase A and A dash, B dash and B, C dash and C. Okay, so 1, 2, 3, 4, 5, 6. So 6 pole, stator 6 poles, and rotor 4 poles. Okay, normally we are arrangement of the rotor and stator, that is like stator pole is a high and rotor pole is a less. So we will get the like high efficiency. So 99% case we can do this type of combination. So stator poles is a very high and rotor poles is a low compared to the your stator pole. The switch reluctance motor, the stator and rotor have projected the pole made upon the soft iron and silicon stepping. So which material we use to stator pole? For the projected pole made soft iron. So we can use the soft iron, otherwise the silicon steppings to design the stator and rotor pole. Silicon stepping is used to reduce the hysteresis losses. So ultimately we have to reduce the any type of losses. Okay. So stator pole, there is an inward the projection. So there is a what we can say the pole diagram of the stator, otherwise the shape of the pole, stator pole, that is a inward projection. So you can see this is the inward projection. Okay, inward projection, and rotor there is a outward projection. So you can see this is the outward projection. Okay. So stator diagram, that is your inward projection, and rotor diagram, that is the outward projection. The rotor does not have a winding. Stator only carry the main field winding. Yes, as I said in the beginning of the class, switch reluctance motor does not have a rotor winding, otherwise the magnet. Each winding in the stator is connected in the series with the opposite pole to increase the MMF. Each winding of the stator is connected to series with the opposite pole of the increase the MMF. It is the called the phase winding referred to figure 1. Correct? Referred to figure 1. So this is the A phase and this is the A dash. Otherwise A complement. Similarly B complement and B. Similar to C complement and this C. So both are the opposite and there is like 180-degree phase shift. Okay. The pole concerned, the number of pole in the stator will be around the 6 to 8 number. Yes, as I said in the previous slide, there is a 6 pole. In the case of the rotor pole will be the 4 to 8. So normally we use the like 4 to 8 ratio, otherwise 4 to 8 pole for the rotor case and 6 to 8 pole for the stator case. By increase the number of pole, we can get the low angle of the rotation from the motor. Yes, suppose you want to increase the number of poles, maybe the stator or maybe the rotor, we can get the low angle of rotation from the motor. The rotor's shaft is mounted with the position sensor. Position sensor is used to determine the position of the rotor by control switch. So it is the same like Hall effect sensor. We use the Hall effect sensor in the case of the BLDC motor. Why use the Hall effect sensor? Because we have to sense the rotor position. Okay. So here is also same. We have to sense the rotor position, and for sensing the rotor position, we have to use the like position sensor. The control circuit is always collect the information of the rotor position, and based on that, controller give the input to the motor. So maybe the based on the rotor position, we have to operate the motor. Maybe the phase A to phase B to phase C. Okay. So you can see the block diagram of the SRM. There is a control block diagram. So this is the input. Input maybe from the battery or maybe the DC supply. It is up to you, correct? So there is a battery or supply voltage, DC supply. Converter circuit. So we can control the like SRM motor. It is the heart of the SRM motor. Digital controller. So we have to use the digital controller. So we can give the command to the converter. So which switch now we have to operate. Okay. And this is the feedbacks. That is your speed. Speed, yeah, maybe the torque. So there is a depend on you which type of control application you are using. Okay. So major component, there is a converter circuit and digital controller. Okay. The DC input is connected to the driver or converter circuit, and the output is connected to the motor. The rotor sensor feedback wire is connected to the controller. So this is your feedback wire. Okay. So maybe this is the position sensor. And it provides the rotor position of the rotor with the reference to the reference axis. Okay. Finally, the controller collect all the information based on that, and reference will be given to the stator. Yes, whatever information is available in the digital controller, that digital controller we can directly feed to the converter circuit, and ultimately converter circuit directly connected with our stator of the switch related motor. Also, the controller monitor the motor current to protect the motor from the internal and external fault. Yes, that is the main role of the controller. So controller also control the like fault current, over voltage, under voltage. Every condition we have to put in the controller. So our motor is working properly. So you can see the converter, typical converter circuit. So this is the phase A. This is the phase B, and this is the phase C. So we can use the normally 3-phase SRM. Okay. So there is a diode. So we can say there is a diode is a unidirectional component, only flow the current from positive to negative, not the negative to positive. So we can use the diode for the feed forwarding operation. Correct. Here maybe the IGBT, maybe the MOSFET, maybe the IGBT, MOSFET, yeah, maybe the transistor. Here is second diode for the phase 1, similarly for the phase B, and similarly for the phase C. So here use of the switch, so there is yes turn on and turn off, and use of diode, there is a feed forward diode. Okay, so during the like energy recovery case, we can use this diode. Okay. So yes, this is the pulses. So this is the phase A, phase B, and phase C. Yes, always there is a on, off. Correct. And second one, there is a maybe the like 90-degree phase shift, maybe the 180-degree, maybe the 30-degree, depend on the control algorithm. Okay. So this switch is we can give there is a pulses to the inverter, and then based on the inverter voltage, that voltage is directly fed to the your stator winding of the SRM motor. Okay. Yes, till now any confusion for the SRM motor? Any doubts, any confusion? Okay. The working principle of the switch reluctance motor is simple. We can take the like iron piece, simple, maybe the iron piece. Okay. If we keep it magnetic field, the iron piece will align with the minimum reluctance. Yes, we can say the current is flowing for the least resistor. Similar, we can say flux is flowing the like least resistor and lock magnetically. So we can say suppose this is your magnetic iron piece. Suppose this is the iron piece, and suppose this is the magnetic, maybe the permanent magnet, north pole and south pole. Correct. Suppose you can slowly go to the nearby the iron piece. Correct. So what happens? So this magnetic field line, that is a follow the like minimum reluctance path. So there is a maximum line is close to the air gap. Okay. The same principle is follow the switch reluctance motor. The minimum reluctance constant of the rotor tries to align itself with the stator magnetic field. So whatever it is a magnetic field is there for the rotor, it is aligned to the stator magnetic field, and motor is low and it is tried to able to rotate for the next pole. Okay. Hence the reluctance torque is developed in the motor. Let's consider the following notation for the better understanding. So which type of notation? That is a stator pole. So we can say A and A complement poles axis for the A phase. So we can say the A that is a positive, and A dash that is your negative. So one is a incoming. So we can say the incoming winding, and this is the outgoing. Okay. So A and A complement, similar for the B phase, there's B and B complemented, similarly for the C and C complemented for the C phase. Okay, so normally we can use the 3-phase motor. Yes, people use the 6-phase motor also. So, but that's a depend on application. Suppose you want the high torque and high power. Rotor poles, there is the A and A complement. Rotor poles axis for the position 1, and B complement. There is a rotor pole axis for the position 2. So please student focus on and concentrate on the A and A capital, that is a stator pole. So capital letter that indicate the stator pole, and A small letter that is indicate the rotor pole. Okay. So you can see the pictorial view. A stator pole, there is A and A complement aligned with the rotor pole, there is A and A complement. So you can see figure number 1. This figure. So you can see the stator A and stator A complement. So both the pole that is aligned with the rotor pole, there is A and A complement. So you can see the exactly aligned with the A phase. And there's a B and C not aligned with the another pole. Correct? So there is a B and B. It is not aligned. Okay. So not now the input is given to the phase A, other B and C phase neither a maximum or minimum. Then stator pole axis A and A complement, and rotor pole axis, that is A and A complement, are aligned as per the figure 1. Figure 2, you can see B and B complement. So this is the B and this is a B complement. Again, that is aligned. Correct? So now motor is operated for the B phase, and then third case, that is a C aligned. C and A complement and C, that is aligned. So now phase C is operate. Okay. So we have to operate this motor by using the power latency converter. Okay. So that's why we have to find out the rotor position. Where is the exact rotor position? Then we can give the pulses to the nearby phase. So that's why motor is able to rotate. Okay. That's why motor is able to rotate. Because of the air gap between the stator and rotor is very less. Yes, you can see the because of the air gap. So there is a phase A, air gap is a very less. And their minimum the reluctance position is compared with the other pole. Then we can say torque is equal to dLA by d theta equal to 0. Where LA there is the phase inductance for the phase A, and theta is the angle rotation. Okay. Similarly, we can say now we operate the motor with the B phase. Correct. So similar, you can see this figure. Correct. So now phase A will be turned off. Now phase A is a turn off. Otherwise, we can say the cut off. And phase B is energized by the external supply. Then rotor axis, that is a B and B complement, is a small letter. It means that is a rotor. Turns to the stator axis, there is a B and B complement. Move clockwise as per the diagram. Yes, you can see the diagram. So there is a like clockwise movement. Correct. First condition is here. Second one, there is a like clockwise direction. Okay. By changing the polarity of the motor, we can easily reverse the motor. Correct? Suppose you want to change the motor direction, so just change the supply polarity. The torque developed since the reductance change from the maximum to minimum. The developed torque is equal to 1 by 2 I square, there is a phase B current, DLB, there is a phase B inductor divided by d theta. Correct? So there is a developed torque is equal to 1 by 2 I square into dl by d theta. The rotor magnet is depending upon the number of poles. In our case, we get the 30-degree rotation by energizing the phase at time. Correct? So that is a 30 degrees is not fixed. Suppose you want to operate like 20 degree, 25 degree, that is up to you because you are designed the control algorithm. So 30 degree, it is a not standardized, it is a not thumb and rule, but that is a depend on you. Yes. Similarly, we can operate the phase C. So now phase B will be the turn off. So in the previous case, there is a phase A will be turn off and phase B is energized. Here is same, phase B is turn off, phase C will be the turn on. Then the torque is developed because of the rotor axis. There is a complement for the rotor. Aligned with the stator axis, there is a C and C complement. The rotor continue to rotate for the another 30 degree. Correct? So another 30 degree again is rotate. So same process we have to continue based on the operation and based on the switching action of the power converter. So you can see there is we can continue operate clockwise direction. Correct? So this direction, and this direction. Continue. We can change the switch position and rotor position. Yes. So what are the advantages of the switch reluctance motor? It does not require any external ventilation system as the stator and rotor slot projected. So by default, ventilation is available for the induction switch reluctance motor. So externally ventilation not required. The airflow maintained between the slot. Correct. The rotor does not have winding, since therefore no need to keep the carbon brushes and slip link. So no need to use the carbon brushes and slip link to collect the current. So because on the rotor side there is no winding, no permanent magnet. Since the absence of the permanent magnet, such motor are available the cheaper, because cost of the permanent magnet is very high. But in the case of the SRM motor, there is no any winding, no any permanent magnet. So we can say it is a very cheaper. Simple 3 or 2-phase pulse generator is enough to drive the motor. Yes, we can use the 2-phase simple, otherwise the 2-phase pulse generator. The direction of the motor can be reversed by changing the phase sequence. So suppose you can change the phase sequence, then easily you can able to change the direction of the motor, maybe the forward direction to reverse direction, otherwise the vice versa. So no need to work on the control algorithm, just change the terminal supply voltage. Okay. Yes, continue. There is advantages. Self-starting and does not require the external arrangement. Yes, you can see in the single phase induction motor is not self-starting. We have to use the both. There is a primary winding as well as the auxiliary winding. Okay. But in the case of the switch reluctance motor, there is a like self-starting. Starting torque can be very high without the excessively induced current. So starting torque is a very high without giving the like high current, because torque is directly proportional to the current. Suppose you can give the like high current, then you will get the like high torque. High fault tolerance, phase losses do not affect the motor operation. Correct? So because at a time we operate like 2-phase, so phase losses do not affect the motor operation. High torque to weight high torque to inertia ratio, and last one, there is a high starting torque can be achieved. So these are the advantages of the SRM motor. That's why people are going to use the SRM motor. Okay, but disadvantages is, what are the disadvantages? Create the torque ripple. Why torque ripple? Because we have to operate continuously switch of the inverter. So that's why there is a very high torque ripple. The external rotor position sensor is required. Yes, for the PMSM BLDC external sensor is required. So there are the disadvantage, but still sensorless it is possible. Noise level is high. Yes, torque ripple is very high. Then we can say noise is a high, vibration is a high. At higher speed, the motor is generate the harmonics. To reduce this, we need to install the large size of the capacitor. So suppose you want to reduce the losses and everything, so we have to install the large capacitor bank. Since the absence of the permanent magnet, the motor has designed to carry high input current. It increase the converter kVA requirement. Suppose you want to design the big size of motor, then it is required the big size of converter also. Okay, so these are the disadvantage of the switch reluctance motor. So key point from the today's class. So that is a working principle of the PMSM and working principle of SRM, as well as the construction, advantage and disadvantage of the PMSM motor. Okay. So key point from the next class. So we will discuss the motor selection criteria for the EV. So which type of motor we have to choose for the EV, for maybe the two-wheeler or maybe the three-wheeler, and motor control techniques. So we will see the fundamental block diagram, overall fundamental block diagram, which we can utilize that control algorithm for the all type of motor, maybe the BLDC, maybe the PMSM, maybe the XRM, okay, maybe the induction motor. So we will see the two to three block diagram for the control of the motor, correct? So maybe we have to control the torque, otherwise maybe we have to control the speed, okay? So these are the few references I already circulated. So research papers, so maybe you can read, okay? So suppose you want to do the more analysis, correct? So because this semester you have to do the project, correct? So suppose somebody is interested to do the project on the motor, then maybe you can read this paper. So thank you so much for your attention. And if you have any question for today's class, please let me know. So I would happy to answer. I will happy to answer your question.
Sir,
Yes, today. Yes.
in SRM motor,
Mhm.
minimum number of rotor pole is always 4 or less than 4.
Always 4.
SRM motor.
Always 4. Minimum.
And rotor and stator pole maybe 6,
6.
8 or any 6.
6. Minimum 6.
Minimum 6, maximum any
Maximum
even number.
any number.
So what will be advantage if the stator pole is increased?
Yeah, here I mentioned now one of the slide. By increasing the number of pole, we can get the low angle of the rotational from the motor. So your speed is less, correct? But you will get the higher torque. And for this comparison, suppose you are interested for, suppose you are increase the number of stator slot, suppose you are increase the number of rotor slot, then what will affect, correct? So suppose you are interested, then what I can do, so in the next class I will make one slide, correct? Suppose you are increasing the number of poles, so that is what is a relationship on the efficiency, what is a relation of the losses, what is a relation of the speed and torque, correct? So I will make one slide for you. So relation between the stator pole and the rotor pole. Is it okay? So you will get more knowledge. Is it okay?
Yes, sir. Right.
Yeah. Any more confusion? Any more doubts from the today's class? Okay, if no confusion, no doubts, then we can close the today's class. But it is my humble request, please submit your assignment as well as the simulation. Correct? Try to do the simulation. Okay. So there is no deadline for the simulation, but please try to complete the simulation work as soon as possible. Okay. So yes, if you no confusion, then we can close the today's class.